Let's talk about waves and the electromagnetic spectrum for GCSE Physics. There are lots of parts of this topic that are for separate science only or higher tier only, so I'll point them out as we go, but this video is suitable for all students at GCSE. So waves look a bit like this, as we see on the left, and we can label a couple of key parts about them. So the first thing to label is the amplitude. That's the top of the wave, the peak, to the middle or the equilibrium point. We would define it as the distance from a maximum displacement to equilibrium. Maximum displacement means just as high as the wave can go. The next thing we can define is our wavelength. Now, wavelength here I've labelled from one peak to another. It can be from any point in the wave to the same point on another wave. So here we could say it's the distance between two peaks on adjacent waves. Adjacent just means waves next to each other. And if we were to label the y-axis, we could label this with displacement being positive and negative about that equilibrium point 0. Another key definition to know with waves is what frequency means. So frequency is defined as the number of waves passing a point per second. You could also say the number of vibrations or oscillations per second. It's measured in hertz, which we abbreviate to Hz. Time period is another definition which we need to know. It's the time taken for one complete wave, and it's also commonly referred to as period instead of time period, and it's measured in seconds. Now, if I was to change my graph up here, the x-axis changing from distance to time, so we're looking at how the wave displacement varies over time. Now, what I had labelled as wavelength is now the time period. Because instead of the length of the wave, it's now the time taken for one complete wave on this graph. The relationship between frequency and time period is that frequency is equal to 1 divided by the period, which will be on your equation sheet for GCSE. Using these two diagrams I've drawn down here, a wave with a high frequency, i.e. lots of waves per second, if it's a sound wave, we describe it as a high pitch sound wave. That means the sound is a little bit higher compared to a low frequency wave, where the wave is a little bit lower, because there are less waves per second. Now, sticking with sound waves, if I was to, instead of changing the frequency or wavelength of the wave, if I was instead to change the amplitude, what we'd notice is that the volume of the wave will change. A higher amplitude wave, like the one here, would indicate a louder wave if we were to measure it on an oscilloscope or something like that, and a lower amplitude wave would indicate a quieter wave. So what this tells us is that amplitude, the more higher the amplitude, the more energy a wave has. In a sound wave, that corresponds to volume, but it could be brightness for light or anything like that, but a higher amplitude means more energy. If I was to multiply together the frequency of a wave and its wavelength, I would find the wave speed, or the speed of the wave, given by this equation here. This is obviously on your equation sheet, but you need to know the units. So frequency is in hertz, wavelength has to be in meters for this to work, and speed of anything we give in meters per second. Now, if you've noticed here, the units don't seem to quite make sense. That's because hertz is a bit of a special unit. Really, what we could say for frequency is measured in 1 divided by seconds, or 1 over seconds, because it's something happening per second. This is the focus of one of the required practicals in this topic, where you measure the speed of waves in water and on a piece of string. So I've linked the video at the top here. Go check that out if you want a bit more detail on that required practical. Next, we're going to look at transverse and longitudinal waves, the two categories of waves. So if I were to draw out a transverse wave, if I draw the oscillations going up and down, so the oscillations or the vibrations that cause the wave will still go left to right. So the direction of energy transfer is in a perpendicular direction to the oscillations. So we'd say a transverse wave, the oscillations are perpendicular to the direction of energy transfer. For a longitudinal wave, if I draw the oscillations as going left to right, the wave will still go in the left to right direction. So what we'd say is that the oscillations are parallel to the direction of energy transfer. You could also say the oscillations are in the same direction as the energy transfer of the wave. Now you notice here that the longitudinal wave looks quite different to a transverse wave. Now here I've given the example as air particles. So in air particles we'll see that the little dots, the particles themselves, are more bunched up in some areas than others. Name we call the parts of waves that are bunched up are called compressions. Where the wave particles are spread out, or the air particles are spread out, are called rarefactions, not to be confused with refraction. Is a different thing. So in terms of examples of each, there are way more examples of transverse waves than longitudinal. Longitudinal, you're basically limiting yourself to sound waves ultrasound waves, and P waves, which are a type of seismic waves, which we'll come on to later. Transverse waves are basically every part of the electromagnetic spectrum, so light, microwaves, X-rays, gamma rays, kind of the lot. Those are the main ones to remember there, plus ripples in water. One really important thing to note about waves is that waves are only ever passed on. So in the example of our hearing, let's say you're to hear a sound in the distance, a drum beating, it's caused by vibrations in the drum skin. That then causes the air particles close to it to vibrate, and their vibrations are passed on and on and on till they reach your ear, which then the vibrations cause your eardrum to vibrate, and then the message gets sent to your brain that you've detected a sound. Note, it's really important to note that the wave does not transfer matter. Waves only transfer energy. So in this case, the air itself isn't rushing into your ear, it's just the vibrations that get passed on. In the case of a transverse wave, if you've got a rubber duck or an animal sitting on the water floating, as the wave goes past, they only travel up and down, and the wave goes past them. They don't travel left to right in the direction of the wave. It's only the energy that's being passed on, not matter or not actual substances passed through the wave. Speaking of sound waves, you can measure the speed of sound in a slightly different way to we talked about earlier with the speed of waves in a string or in water. We can use the equation speed equals distance divided by time to work out the speed of sound. Now this is kind of tricky to do because to measure the distance you need really large distances, way over 100 meters, and to measure the time taken you need very good reaction times. So to do this yourself you need to measure a really large distance, and you need to bang a drum or some other object that's large enough for you to see the sound that's taking place, or see the bang of the drum that means the sound is taking place, and you time the difference in time between you seeing the sound and you hearing it. You might have noticed that with fireworks or other objects that are far away, you will always see the object first rather than the sound. So if you could time the difference between those two events, seeing and hearing it, and the distance between you and where the sound is coming from, you could work out the speed of sound. Now the speed of sound in air is roughly 330 meters per second. However, it will travel faster in a solid. That is because particles in a solid are closer together. The sound won't necessarily be clearer, but it will travel faster because there is less distance between the particles for the sound to travel in. When a wave hits a barrier between two different substances or two different media, the following can happen. So in an example of when a wave travels from air to glass, the wave could be reflected, it could be absorbed, or it could be transmitted, or more likely a combination of any of these things. So let's look at the first one then, to look at what happens when a wave gets reflected from a surface. So in the example of light, the most common surface it's going to reflect from is a mirror. So when light hits a mirror, we draw a ray diagram. The ray diagram must have arrows on it to show which direction the light or the wave is travelling in, and it must be in straight lines. So when the wave hits the mirror, we can draw on something called a normal, which is normally represented by a dotted line, and it's always a 90-degree angle to the point where the wave hits the surface. So in this case here, it comes out towards the left. So when the wave hits the mirror, we can label on something called the angle of incidence, represented by the letter I here. We'd measure that with a protractor, and it helps us determine the law of reflection. So when the ray comes out, the angle it makes with the normal, which is called the angle of reflection, is going to be exactly equal to the angle of incidence. So that's the law of reflection, which is to say the angle of incidence is equal to the angle of reflection. If I was to introduce an observer, someone who could see the light coming from the mirror, to the observer or the person looking at it, it would look like the object is sort of behind the mirror. So if you trace the rays of light back from the person's eye past the mirror, it looks like the object is behind the mirror. So that means the object, the image, we say is virtual. It's not actually there. The eye is sort of playing a trick. So reflection and what we're going to look at next, refraction, are examples of higher tier topics, not separate science only, but topics you'd only find on a higher tier paper. So refraction is an example of what happens when a wave gets transmitted through a different material. Transmitted sort of means just let through. So what happens with refraction, let's go from air into glass this time rather than a mirror, is that the ray of light changes direction. Now we can draw the normal on here. This time the normal extends into the glass block, still at 90 degrees, and we can see that actually it bends towards the normal. So why does this happen? Well, to explain it, we've got to use something called wave fronts. So what I'm drawing here are perpendicular lines to the direction of the wave called wavefronts. Each one of them represents a peak of a wave. It's just another way of representing a wave. Just like I've got the sort of loopy up and down wave here, we can also represent it as these horizontal lines. So if I've got a wave that's traveling from air into glass, I'm going to draw the wavefronts traveling along. Now hopefully we can see that because it's traveling at an angle, the wave would actually reach the glass at different times. Now when a wave hits a more dense medium, like for example going from air less dense to glass more dense, it's going to slow down. But if we look carefully, the side here on the left hand side of my drawing, the drawing of one side of the wavefront will slow down first, while on the other side that will not change initially, that will keep on going as it is. Then when we enter into the glass block, eventually the whole wave has now turned so that it's traveling a little bit more towards the normal. It's worth noting at this point that the diagram would not look the same if the wave wasn't traveling at an angle. If it was traveling perpendicularly to the surface, nothing would happen, it wouldn't change direction. It's all because it travels at an angle, one side of the wavefront hits the surface first. Now, if we were to measure the angles going into and out of the boundary, what we'd find is that from the angle of incidence, from the normal to the incident ray, that angle of incidence is going to be bigger than the angle of refraction. That's because the wave is traveling towards the normal. So this is part of one of the required practicals if you do separate science for refraction of light through a glass or a perspex block. For the wave exiting, so if we go in the opposite direction, this time from glass to air, we're going from a more dense to a less dense material, so this time the wave bends away from the normal. Now that would mean that the angle of incidence, so this one at the bottom here, is actually going to be bigger than the angle of refraction. Another thing we can note from this diagram is what's happened to the wavelength. So the distance between the wavefronts represents the wavelength, and hopefully we can see from the diagram that inside the glass block the wavelength has decreased. Now it decreased because the speed has decreased. Those two things are going to be directly proportional. If we go back to our wave equation, speed equals frequency times wavelength, the frequency doesn't change. So if I decrease the wavelength, the wave decreases in direct proportion. This effect can also be seen in water. If you travel from deep water to shallow water, the same thing will happen. You'll find refraction occurs and the wavelength will change, again getting shorter in shallow water. The next section of the video is for only if you study separate science only. So we're going to look at ultrasound and also seismic waves. Then come back for the electromagnetic spectrum, which even if you're doing combined science, you do need to know about. So ultrasound defines a wave that is a sound wave greater than 20,000 Hertz in frequency. This is outside the range of human hearing. Some animals can hear outside this range, but humans can't, so we call it ultrasound. Its most famous use is in fetal scanning, or scanning fetus while it's in someone's womb, but it can also be used to scan for cracks in materials in industry and also for cleaning things like dirt off watches. It's very similar to something called sonar, which it doesn't use ultrasound but uses sound waves to detect things like how deep a seabed is. I'm going to use this example to help explain ultrasound because it's easier to draw, but it works in the same way. So let's say I've got a ship on the surface of the water. It wants to find out what the depth of the seabed is to know where to place its anchor or when to go into port. So what it's going to do is it's going to emit a sound wave downwards, and the sound wave is going to reflect back up, or an echo. What the ship can do is it can measure the time taken for that sound to return to it, and you can use it to work out the distance, or in this case the depth. So from our equation from earlier, distance equals speed times time. The distance is going to be the depth, the speed is the speed of the wave, which is a known quantity, and the time taken is what's measured. But because the time taken is the time taken for the sound to bounce back, that's actually going to be double what the depth is. So we would have to halve the time so we could find the accurate value for the depth. Now this works in the same principle when you're scanning a fetus inside the womb. The ultrasound will reflect back from a boundary between two different media, and then the time is measured, and then you use distance equals speed times by half of the time, and then the image is formed on a screen doing this like sort of thousands of times per second to be able to form an accurate image of this very beautifully drawn fetus inside the womb. Lastly, for this little section, let's look at seismic waves. So seismic waves are waves caused by an earthquake or some sort of volcanic activity. There are two types of seismic waves. There are primary waves, or P waves, and there are secondary waves, or S waves. As the name suggests, the primary waves arrive first, so they're faster. The secondary waves arrive second, so are slower. Now we need to know that primary waves are longitudinal waves, but secondary waves are transverse waves. Now because they're transverse and inside a solid, that means they do not travel through liquids. So S waves do not travel through liquids, really important fact to remember. When we're talking about earthquakes traveling through the Earth's core, P and S waves therefore travel in different ways. So if I've got my purple P waves here traveling through the Earth's core, they can sort of travel through any part. So on the other side of the world, you'd be able to detect P waves. They will refract slightly because they're going from one density of core to another, hence why they are sort of curving and changing direction here, but they'll still reach the other sides. In contrast, S waves we can only detect at certain areas in the Earth. Where you don't detect S waves, you find something called a shadow zone because they do not travel through the core. So this means that because S waves don't travel through the core, we don't detect them. One conclusion, or the only conclusion we can draw, is that the Earth's core must have liquid parts to it, so S waves can't travel through it. So this allows us to find out what's inside the Earth without actually going there. A really good example of using science and using physics to find out about something which we can't see. Electromagnetic waves form the electromagnetic spectrum, abbreviated to EM spectrum. As long as you write down two capitals, you can always abbreviate it to EM. So electromagnetic waves are made up of these 7 parts. We've got radio waves, microwaves, infrared, visible waves, ultraviolet, X-rays and gamma rays. Now hopefully it's obvious, but the only part we can see and directly detect as humans are visible rays. So we need to know what the order of these different waves are. A helpful way of remembering it, there are lots of different ways. My favourite is the one on the right hand side here, which is rabbits mate in very unusual expensive gardens. Your brain's more likely to remember a silly little scene, but anything you can do to remember the order of those 7 different parts of the spectrum would be perfect. Now, electromagnetic waves are made up of oscillating electric and magnetic fields. You're unlikely to find a question on that, but a lot of people ask me, well, what causes them? It's oscillations, but it's in these electric and magnetic fields. Something you could get asked about is what speed they travel at. So they all travel at the speed of light, or visible light, which is 300 million meters per second, or 3 times 10 to the power 8 meters per second. Obviously very, very fast. Now all these different parts of the spectrum have different uses, which I'm going to list here. These are directly from the AQA specification, but it'll be okay for all exam boards to learn what the use is for each one. So radio waves are used for TV and radio. Microwaves are used for cooking food, obviously in a microwave oven. Both of them you can say they're used for communications. Infrared is used for thermal imaging and electric heaters, or heating anything up like food using a barbecue or anything like that. Infrared radiation is basically just heat. Visible light is used obviously for seeing, but also for fiber optics and also for things like CDs and DVDs. Ultraviolet is used for suntans in suntan beds or tanning beds, and also for energy efficient bulbs. X-rays are used for medical imaging, so to detect any broken bones. Gamma rays are also used for imaging, but also radiotherapy and sterilizing medical equipment. Well, one thing that's really useful to do for the sort of really high ability, high level questions is being able to link some of these uses to the properties of electromagnetic waves. Now, you can see I've written down here, I've got the right-hand side of my diagram where gamma rays lie. It's low wavelength and high frequency. It's all to do with these properties of the waves that makes them different and also makes them useful for different things. So, for example, if I'm going to use X-rays and gamma rays for medical imaging, they need to be able to go penetrate inside the body. Now, for example, gamma rays have a really small wavelength, which is smaller than the gap between cells and atoms usually as well, so it allows them to penetrate inside the body. Some parts of the electromagnetic spectrum can be dangerous. It's only the ones that have a higher frequency than visible light that can be really dangerous. So that means there's ultraviolet, X-rays and gamma rays. They're dangerous because they are known as ionizing radiation. Ionizing radiation means if it gets into your body, it can mutate genes in cells and it can also cause cancer. In particular, ultraviolet waves can cause skin cancer or can cause it to age prematurely, and gamma rays are the most dangerous in this regard because they are the most ionizing. Despite these types of radiation all being dangerous to an extent, they're useful to make things like X-rays. So if I was to compare the dose received by an X-ray, by a radiotherapy session, and by a sunbed session, we can analyze and compare the danger from their dose. So the dose we're using here, the units, is in millisieverts. So sieverts is the unit for dose, so you don't need to memorize it, but be familiar with it. And milli means 1,000th. So if I was to compare all these to the fatal dose, the dose needed to kill you, which is 5 sieverts, you can see that all of them, to different degrees, are far lower than the fatal dose. So we'd say that actually they're something to be aware of, but not dangerous, as they have a fairly low risk. But it is the reason why you can't have unlimited X-rays in 1 year, for example. Now, electromagnetic waves are all caused by changes in atoms. If you've watched my video about the Bohr model, we'll know that electrons exist in shells, but they can change between shells. When they drop from a higher energy shell to a lower energy shell, they emit electromagnetic radiation, or an EM wave. Gamma rays are emitted from changes in the nucleus, not in the shells of electrons. The last part of this topic on the electromagnetic spectrum is for higher tier students only, and it is a tricky one, but it comes up a lot in exam papers. A question might say, how are radio waves transmitted from a transmitter or received at a receiver? So from a transmitter, what happens, you have a metal which have free electrons. The electrons are caused to oscillate. When electrons oscillate at the right frequency, they produce a radio wave. So we'd say the alternating current in the transmitter causes radio waves to be emitted at the same frequency as the alternating current. Next, these radio waves make it over to our receiver, which looks very similar to our transmitter. This time, it's not the electrons that oscillate at the start, but it's the radio waves are absorbed. They cause the electrons to oscillate and therefore alternating current to be induced. So we say the radio waves are absorbed, they produce an alternating current at the same frequency as the radio waves. And that could be around 3 marks, so it's worth memorizing that word for word, I would say. There are 7 parts to the electromagnetic spectrum, but in this video we're only concerning ourselves with one. That's visible light, or the light we can see. So this ranges all the way from red down to violet, via orange, yellow, green, blue and indigo. So the red end of the spectrum, the violet end of the spectrum, the violet end has the highest frequency but the lowest wavelength. Red end of the spectrum has the opposite. It has the lowest frequency, and that means it has the highest wavelength. One of the things light can do is reflect. So we're going to look at 2 different types of reflection. The first one is something off a flat surface, a very polished surface like a mirror. This would be called specular reflection, and that means the rays of light hitting the mirror parallel to each other also leave the mirror or surface parallel to each other, and that enables images to be formed. The other type of reflection is from a more rough surface. This is called diffuse reflection. So as you can see, the rays of light enter the mirror parallel to each other, but they exit at different angles because the surface is rough. It does not reflect them evenly, so they end up being scattered. So this would be any rough surface that's not a polished mirror, so clothes, carpet, walls, anything like that. So for this part of the video, we're just looking at diffuse reflection. We're not necessarily looking at mirrors, we're looking at surfaces and what colours they might absorb or reflect. So if I have white light, which if we don't know, it contains all colours, if that hits the surface, and if only the red part of the spectrum is reflected, with orange, yellow, green, blue, indigo, violet being absorbed, that shows us that the colour is red. So the colour of the object is red. And if I was looking at that object, you would see it as red because it's only reflecting red light. In another example, we've got white light incident on this surface down here. Let's say we've got red being reflected and all the blue parts of the spectrum being reflected, so blue, indigo and violet, but orange, yellow and green absorbed. So what that would mean is that would combine the reds and the blue colours together, so the object would be purple, as it's reflecting both red and blue light, so they combine together, in this case, to make purple. If we have no light being reflected, so in this example here, all the white or any colour is absorbed, that shows us the object is black or appears black, because there's no light reflected and all colour is absorbed. If I shine blue light onto a red surface, and we know it's a red surface already, if there's a red surface with blue light incident on it, it's not going to reflect any light. Red surfaces only reflect red light, so if there's no red light incident on it, it cannot reflect it. So therefore no light's going to come off it. If you were viewing it from afar, you would say it appears black because it's not reflecting any light. Next, let's talk about filters. So filters don't allow light to be reflected, they allow light to be transmitted. So let's have white light going through a red filter. Now a red filter will transmit red colours, but it will absorb all other colour wavelengths. So that means in this case that the red light goes through, but all the other colours are absorbed. If we were then to put this red light through a blue filters do the same thing, but they only transmit blue, and they'll absorb all the other colours. So because it's not white light hitting this filter, it's only red. That means that it's going to absorb the red, but there's no blue light for it to transmit. So therefore it's not transmitting any colours at all. It's absorbing all the light that's incident on it because it's just red. If you were to view from the other side of this filter, the object, let's say coming from the white light from initially, again it would appear black. Next, we're going to consider a couple of key definitions, which are in general, if I've got all light being transmitted through a surface, we call it transparent. If there's only some light being transmitted, we call it translucent. And something that's called opaque means that no light is being transmitted at all through it. Next, we're going to look at lenses. So there are two types of lenses you need to know. There are convex lenses and there are concave lenses. Now, the way to remember it is concave is sort of bends inwards at the middle, looks a bit like a cave, whereas convex is the other one. You also need to be familiar with the symbols for each, which I've drawn here. So convex has another name. Convex, the other name for it is a converging lens. As you can see the rays of light here, they enter the lens parallel to each other, but they converge to a point or a focal point. Concave lenses are known as, on the other hand, diverging lenses. That's because the rays of light that enter parallel to each other will diverge or get further apart from each other. And the symbol I've drawn here as well. So we need to be able to draw lens ray diagrams to be able to figure out what images will look like once they go through some of these lenses. So let's set up our ray diagram. We've got a horizontal line, which is called the principal axis, and we're going to set up our lens. I'm going to use the symbol for the convex lens in the middle. I'm going to draw a focal point, capital F, on either side of the lens. They should be equidistant from each other. This will normally be done. I'm going to set up a focal point on each side of the lens. This will normally be done in an exam question for you. And the distance between the focal length and the lens is known as the focal length. So I'm going to represent my object as an arrow. It could be anything, it could be a tree, it could be a person, but an arrow is simplest to draw. So the first ray of light we draw, both of them are going to come from the top of the object. The first ray of light is going to go horizontally from the top of the object through the lens, then it's going to refract and it's going to go through the focal point on the other side. Don't forget, lenses are made from transparent materials so that it refracts, light can bend. The other ray of light we're going to draw is going to go through the center of the lens, and this one isn't going to change. This is because if it's going through the center of the lens, it is entering the lens roughly normal to the lens, i.e. perpendicular, so it won't refract as it goes through it. And we draw it going out the other side in a nice long continual line. So the image gets formed where the rays of light cross over. So in this case, as we can see, if I'm drawing the image in here, it's actually upside down. The top of the image has to still be where the rays of light cross over, because that's where they've come from. So we describe this image in three ways. The first way is to say it's inverted, meaning it's upside down. It's also a little bit magnified, not too much in this diagram, but it's got a little bit bigger, and it's a real image. Real image means the rays of light cross over after a lens or a mirror, and they can be projected onto a screen. If I was to put a screen there, then this would be what's formed. An example of this would be like a cinema screen when you're projecting something from a projector. The next example we're going to look at is a convex lens, but the object is much closer. So as I'm setting my diagram, the object is further in, closer to the lens than the focal point on the left-hand side. So let's draw my rays of light in. My first ray is going to go parallel to the axis, horizontally, through the lens and then through the focal point. My next ray goes through the center of the lens, just like before. But we notice something weird happens. The rays of light are not going to cross over on the right-hand side of the lens. So therefore we can't have a real image being formed. If I was to observe the image from the right hand side, so after the lens, we don't get a real image. So therefore we have to trace the rays of light back so we can find a virtual image. So if I trace these two rays of light back, they go quite far back and the image ends up being quite large because the rays of light have been traced back so far that the image has got a lot bigger. So we describe this image as upright because it's not upside down, it's magnified, it's a lot bigger, and it's virtual, meaning the rays haven't crossed over so it can't be projected onto a screen. An example of this would be in a magnifying glass because it makes a virtual image of an object much, much bigger than it actually is. And to calculate magnification, we need to know the object height and the image height, just like you would need to know in biology. The last lens we're going to look at is our concave lens. Now there's only one type of diagram for this. So if I set up my diagram with my symbol for the concave lens just like I did for my convex lens, it doesn't matter where the object is for this, all the diagrams look the same. So I'm going to have my ray of light going first of all from the top of the object horizontally to the lens, but this time it's not a converging lens, so the ray of light doesn't go down through the focal point, it's actually going to converge away from the other rays of light. But I've got to be careful how I do this. I draw it going away from the rays of light, but it's got to be in line with the focal point on the left-hand side of the lens. So I'd say it's horizontal to the lens, but you sort of trace it back through F. I would do a dotted line to indicate it's not a real line, it's not a real ray of light. The second rule is unchanged. That still goes one ray of light through the center of the lens, through the center of everything. Now hopefully we should note that the two rays of light don't cross over on the right hand side of the image. There's no real image formed, but they do cross over with one of the virtual rays, or the rays I've traced back. Now this image is therefore upright, it's diminished, meaning it's quite significantly smaller, and it's a virtual image for the same reason as previously. The real rays of light have not crossed over. So an example of this would be a telescope, which takes really big objects and makes them really small in telescopes for us to be able to see. And that's our concave lens. Each of those diagrams would be 3 marks for the drawing of the rays if you draw them in the real exam. Lastly, for this separate science only video, we're going to talk about blackbody radiation. Now this is something that's unique to the AQA specification from what I'm aware, but even though it sounds a bit scary, a bit weird, trust me, it's not too bad. So let's say we've got a cup or a mug of water, for example, and I've got a heater. So if I was to provide it with some heat or some infrared radiation in, and it's going to re-emit some of that back into the surroundings. Now, if there is more infrared radiation in than there is coming out, that means the temperature of the mug or of the liquid will increase. If I was to reverse it and there's more infrared or heat coming out than going in, the temperature would decrease. And if they are equal to each other, the temperature will stay constant. Now, this can be applied to things like planet Earth. So for the Earth's temperature to increase, and this is how basically the basics of how global warming works, there must be more radiation being absorbed than there is emitted. And instead of saying radiation or waves come in and go out, we should be using those key terms. They're really important. So for example, for my cup of water or tea earlier, we'll say radiation absorbed and radiation emitted instead of in and out. Now, we need to know what this thing called a blackbody is before we can understand blackbody radiation. So a perfect blackbody is defined by something that absorbs 100% of the electromagnetic radiation incident on it, or that is going into it. It also emits or re-emits 100% of that electromagnetic radiation, hence why it's known as a perfect blackbody. Now, it's worth noting that blackbodies don't really exist in nature. They're just a sort of hypothetical that help us make assumptions to calculate different things. They're not a real thing, but there's something in physics that is very important when we look at things like heat. The last thing for this topic is to look at how the intensity of the EM radiation emitted varies depending on the temperature. So generally speaking, over all the different wavelengths, you're going to have a higher intensity for hotter materials versus those for colder. They're all going to emit radiation, but at different intensities and different wavelengths. So we say that different temperatures will emit electromagnetic radiation at different wavelengths and different intensities. For example, the peak of this hotter emitter might be in the UV range, whereas in the colder might be in the visible light range, just like you'd find for different temperatures of Bunsen burner, the different wavelengths are emitted. The hotter one emits blue light, the colder one emits more sort of orangey red light. And that's blackbody radiation. I hope you found that helpful, and please leave it a like if you did so, and keep an eye out for more content coming soon.